Welcome back. Let's learn about the cross product. All right, so earlier in Calculus 3, we asked the question, can we multiply two vectors together? And we said that the answer was yes, but that there's two different ways for us to go about it. We already looked at the first way, which is the dot product. The dot product of two vectors resulted in a scalar value, but now what we want to do is look at the second way of multiplying vectors together, which is the cross product. And unlike the dot product, the cross product of two vectors is going to result in another vector. Okay, but before we can take a look at that, before we can see how to perform the cross product, what we need to do is first review how we calculate determinants of 2x2 and 3x3 matrices. And I know that that might seem a little bit random, like it has nothing to do with vectors, but I promise that understanding how to calculate determinants is going to be helpful for learning the cross product. And you will see that later in this video. But for now, let's quickly review how we calculate these determinants. And let's start with a 2x2 determinant first. To calculate the determinant, what we kind of do is cross multiply in a way. We multiply a1 by b2, and then we subtract multiplying a2 by b1. All right, so that looks like this. We have a1 times b2, and then we subtract a2 times b1. Okay, so we multiplied a1 by b2, that's right here, and then we multiplied a2 by b1, which is right here. And so the result of this calculation is the determinant of a 2x2 matrix. But now for a 3x3 determinant, things get a little bit more complicated, but it's not too bad. What we're going to end up doing is breaking up a 3x3 determinant into three separate 2x2 determinants. And so here's what I mean by that. What you want to do is look at the first row of your matrix. All right, so the row where we have A1, A2, and A3. We're going to start by looking at A1. We're going to be multiplying A1 by a 2x2 determinant. And the way we find that 2x2 determinant is by covering up or crossing out the row and the column that A1 is located in. And then the four remaining values are what we're going to use to calculate a 2x2 determinant that we then multiply by A1. All right, so here's what that looks like. We're going to have a 2x2 determinant using B2, B3, and then C2, C3, and we're multiplying that determinant by A1. Okay, so we're looking at A1 in our first row here, and we're covering up the row and the column that that value is located in, and then using the remaining four values to create this determinant or matrix that we then calculate the determinant of and multiply it by A1. Okay, but now that's just one part of the 3x3 determinant. There's two more parts. The next part we subtract. We're going to be subtracting another determinant, but now multiplied by A2. We're moving on to the next value in this first row. And so just like with A1, what we're going to do is cover up or cross out the row and the column that A2 is located in, and then the remaining four values are going to create a matrix, a 2x2 matrix, that we are going to calculate the determinant of and multiply by A2. All right, so in this case, we're going to have B1 and B3, and then C1 and C3, and the determinant will be multiplied by A2. So that's the second part of our 3x3 determinant, and then we have one more part, and this part is added. This is just a definition of a 3x3 determinant. We subtract the second term, but then add the third one. We're going to have another 2x2 determinant, but this time it's going to be decided by our third value in the first row, which is A3. All right, we're going to be multiplying this determinant by A3. And so once again, to determine what values will be in this matrix or in this determinant, we're going to be looking at our value of A3, but then we're going to cross out the row and the column that it's located in, and then the remaining four values will make up that matrix that we will calculate the determinant of. All right, so we're going to have B1 and B2, and then C1 and C2. Okay, so we calculate that determinant and then multiply it by A3. And that right there, these three terms will give you the determinant of this 3x3 matrix. Okay, for each of these 2x2 matrices, you would perform this calculation right here. So we'd have B2 times C3 minus B3 times C2. then you'd have b1 times c3 minus b3 times c1, and then you'd have b1 times c2 minus b2 times c1. Okay, and so that's all the reviewing that we're going to do here. That's how you calculate the determinants of a 2x2 and 3x3 matrix. So just kind of keep that in the back of your mind for now, because we're going to come back to this in just a little bit. But now that we have reviewed these calculations, we are now ready to take a look at how to calculate the cross product of two vectors. All right, so here's the definition of the cross product for two different vectors, vector v and vector u, which are both three-dimensional vectors. They both have x, y, and z components. The components of vector v are v1, v2, and v3, and the components of vector u are u1, u2, and u3. For those two vectors, vector v cross vector u, or the cross product of those two vectors, is equal to the following vector, right? This is a vector. We have some value multiplied by vector I, our standard unit vector, in the x direction. So this is our x component. Then we have another value multiplied by j, our standard unit vector, in the y direction. So this is our y component of the vector. And then we're adding another value, but this time multiplied by vector k, our standard unit vector in the z direction. So this is our z component of our vector. All right, so the cross product of these two vectors is another vector, but as you'll probably notice, the components of this vector are kind of complicated, right? The x component is v2 times u3 minus v3 times u2. The y component is v3 times u1 minus v1 times u3, and the z component is v1 times u2 minus v2 times u1. That seems like a lot to remember. And so while this is the definition of the cross product of two vectors, we're not really ever going to use this definition. Instead, what we're going to do is represent the cross product of two vectors in determinant form, which will make memorizing this formula completely unnecessary. All right, as long as you know how to calculate determinants of 2x2 and 3x3 matrices, the cross product becomes a very simple process. And so let's take a look. How are we going to do that? How are we going to take the cross product of vector v and vector u using determinants? Well, here's what it's going to look like. First of all, let's write this down. We'll have vector v cross vector u, and then what we're going to do is represent this calculation with a 3x3 determinant. Now the first row is just going to involve our standard unit vectors. All right, so we're going to have vector I, then vector j, and then vector k. Okay, the first row is our standard unit vectors. Then the second row is going to be the x, y, and z components of the first vector, right? If we have v cross u, then vector v is our first vector, and vector u is the second vector. So we're going to write in the components of vector v next. So we'll have v1, v2, and v3. And then for the third and final row, we're going to use the components of the second vector, vector u. So we'll have u1, u2, and u3. Okay, that is going to be our 3x3 matrix that we are going to take the determinant of that will give us the cross product of these two vectors. And it might not be initially clear how the determinant of this matrix will be the same as this result right here, but you're going to see that they are the same if we try and calculate the determinant of this matrix. So let's do that. Remember that for a 3x3 determinant, we're going to be looking at the first row here, starting with vector I, and we're going to be multiplying vector I by a 2x2 determinant. And that 2x2 determinant is determined by the values left over when we cross out the row and the column that vector I is located in. As you can see, what's left over are these four values. Those are going to make up our 2x2 matrix that we will calculate the determinant of. So we'll have a 2x2 matrix, or 2x2 determinant, using v2, v3, and u2, u3, and that's going to be multiplied by vector I. Then we're going to subtract the second term. And by the way, if you're looking ahead, don't get caught up on this negative. I know right now it seems like that is contradictory to this plus sign we have for the second term here. Don't worry, things are going to even out here. Just hang on for a little bit. But we're going to be subtracting that second term where we'll have another 2x2 determinant, but this time it's going to be based on vector j, the second value in our first row. What we want to do is cross out the row and the column that vector j is located in, and the remaining four values will make up our 2x2 matrix that we will take the determinant of. All right, so we'll have another 2 by 2 matrix. This time we're working with V1 and V3, and then U1 and U3. And the determinant there will be multiplied by vector j. Okay, then we have one more term. We're going to be adding this to one more 2 by 2 determinant, but now multiplied by vector k. All right, so once again, we're going to cross out the row and the column that vector k is found in, and the remaining 4 values will make up our 2 by 2 determinant, or the matrix that we're going to calculate the determinant of. So let's write that out. This time we are working with V1 and V2 and U1 and U2, and that determinant will be multiplied by vector k. Okay, so this represents the determinant of this 3 by 3 matrix that we made. That's going to give us the cross product of vector v and vector u, but it's still not clear how this is the same as what we have right here. So we need to take it one step further. We need to actually write out the determinants for each of these 2 by 2 matrices. All right, so remember, we do a little bit of cross multiplication here in a way. We'll multiply v2 times u3 and then subtract v3 times u2, and we'll do the same thing for each of these other 2 matrices. All right, so here's what this is going to be equal to. We're going to have v2 times u3 minus v3 times u2. All right, and that is going to be multiplied by vector I. Okay, so we multiplied v2 times u3, and that's right here. And then we subtracted v3 times u2, which is right here. Okay? Now we're subtracting the next determinant, and this time we're going to have v1 times u3 minus v3 times u1. All right? And that will be multiplied by vector j. And so once again, we took v1 times u3 right here, and then we subtracted v3 times u1, which is right here. All right? Then finally, we have one more determinant to calculate. This time we'll have v1 times u2 minus v2 times u1. So I'll write v1 times u2 minus v2 times u1. And that will be multiplied by vector k. And now, take a look at what we have here. The resulting vector is pretty much identical to this definition of the cross product that I gave you to start with. The only difference is that middle term. If you take a look, it seems like they are completely different terms, right? Because we have plus this quantity times j, but now we have minus this quantity times j. But they are actually the same because if you take a look at the terms that we're subtracting, they are in the reverse order, right? We have v3 times u1 minus v1 times u3, but down here we have v1 times u3 minus v3 times u1. So the order of those two terms swapped, which means if we were to reverse them here, a negative would come out and it would be positive anyway. And if you're not following what I mean by that, let me show you up here real quick. In a more general case, if we have x minus y, that is the same as y minus x, but negated, right? Because if you distribute that negative sign through that quantity, you'll have negative y plus x. So then you can reverse the order and you'd have x minus y right here. So it's the exact same thing between this term and this term. The two values are reversed in their order, so pulling out a negative sign will make them the same. All right, so that's how they are the same. This definition of the cross product is exactly the same. It's equivalent to calculating the cross product using a 3 by 3 determinant. Okay, and so that's the method that we are going to use to calculate the cross product of two vectors. Setting up the cross product as a 3 by 3 determinant is going to make it so that you don't have to memorize this definition of the cross product. You can simply just calculate some determinants and get to the same result, but without any unnecessary memorization. Okay, but now before we take a look at an example problem where we actually calculate some cross products of vectors, there are a couple notes about the cross product that I want you to be aware of. All right, so a couple things to know about the cross product. First of all, the cross product is not defined for two-dimensional vectors. We can only perform the cross product for vectors in 3D, so just make a note of that. There is no two-dimensional cross product. And then the next thing we already talked about, but the cross product gives a vector, right? When you perform the cross product on two vectors, the result is another vector. And what that vector represents is what these last two notes about the cross product are about. If we cross vector v and vector u, the vector that results is a vector orthogonal to both vector v and vector u. All right, in other words, the result is a vector that is perpendicular to both of those vectors that we multiplied together via the cross product. And in the same way, the reverse of that cross product, vector u cross vector v, notice that the order is reversed, the vector that results from that cross product is also a vector orthogonal to both vector v and vector u, but it will be in the opposite direction as v cross u. Okay, so now to kind of help you visualize what we're talking about here, let's say that this is vector v and this is vector u, and they have some angle between them. Regardless, these are two vectors in three-dimensional space. The vector that results from vector v cross vector u would look like this. All right, this vector right here is vector v cross vector u, and it's perpendicular or orthogonal to both vector u and vector v. All right, it makes a right angle with both of those two vectors. Now, vector u cross vector v, the reverse of that cross product, is also a vector orthogonal to both vector v and vector u, but it will be in the opposite direction. So that vector will look something like this. This vector would be vector u cross vector v. It's the reverse cross product, and so it still creates a vector that's orthogonal to both vector v and vector u, but it's in the reverse direction of v cross u. All right, so that vector still makes a right angle with vector v and with vector u. Okay, so hopefully that helps you visualize the result of the cross product of two vectors. It gives you a vector perpendicular or orthogonal to both of the vectors in that cross product. But now actually determining the direction of that cross product, whether it points one way or the other, you can actually determine by using what is known as the right-hand rule. Or in other words, just by using your right hand. And I'm going to show you this here, and this might be a little jarring. My hand is going to appear on the screen right now, so don't freak out. But I kind of have to show you my actual hand in order for you to understand the right-hand rule. All right, so here's my right hand. I'll wave hello. Hello. Okay, but here's how the right-hand rule works. What you're going to do is you're going to point your hand in the direction of the first vector of your cross product. So if we're doing vector v cross vector u, I'm going to point my hand in the direction of vector v, and then what we're going to do is point the palm, my palm, that's this part of my hand, I'm going to point that towards vector u, all right? And then wherever my thumb is pointing, in this case it's pointing up naturally, wherever that's pointing, that is the result of v cross u, okay? So you can see that the direction of that vector is pointing upwards. Now, in the opposite direction, if I want to do vector u cross vector v, what we want to do is line my hand up so that I'm pointing towards vector u, but then the palm of my hand needs to be pointing towards vector v. So I want to flip my hand, so now my palm is pointing towards vector v, and this kind of hurts a little bit, but anyway, my palm is pointing towards vector v, and now you can see that my thumb is pointing downwards, which is the direction of vector u cross vector v. All right, so that's kind of how the right-hand rule works. That's how you use your hand to determine the direction of the cross product of two vectors. I'm not sure how often you will end up using the right-hand rule throughout Calculus 3. Typically, it's something that becomes a lot more helpful in a physics course, but I thought I would at least show you it because it can be helpful in some situations. Okay, so those are all my extra notes on the cross product that I wanted you to be aware of. And so now I'll wave goodbye and we'll move on to our first example problem of calculating a cross product. All right, so here's our example problem. We want to find vector v cross vector u and vector u cross vector v if vector v is equal to negative 4i plus j minus 2k and vector u is equal to I plus 3j plus k. All right, so we want to calculate two cross products here, one of v cross u and then the reverse of that, u cross v. And there is a trick to doing that second one quickly once you have the first one, and we'll talk about that in a second. In fact, you might already know what I'm referring to if you think back to what we just talked about regarding the direction of our cross product vectors. But let's just start by calculating the cross product of vector v and vector u using our 3x3 determinant. All right, so we're going to set up a 3x3 matrix here. Our first row will be the standard unit vectors. So we have I, j, and k, and then the second row will be the components of vector v. So we have negative 4, 1, and negative 2. those are the coefficients of I, j, and k. So those are our components and the values that will be in that second row of our matrix. So we'll have -4, 1, and -2. Okay, and then the third row will be the components of vector u, which are 1, 3, and 1, the coefficients of I, j, and k. So we'll have 1, 3, and 1. Okay, and so now let's calculate our determinant here. We're going to start by looking at vector I. We're going to cross out the row and the column that that vector is in, and the remaining values here will make up our 2 by 2 determinant. So we're going to have a determinant of 1, -2, and then 3, 1, and that is going to be multiplied by vector I. Then we will subtract. Remember, you always subtract the second term where you're going to be multiplying by vector j. You always want to subtract that, and we're going to have another 2 by 2 matrix. We look at vector j, but then cross out the row and the column that vector j is in, and then the remaining 4 values will make up our 2 by 2 matrix that we'll use to calculate the determinant. So we have -4, -2, and then 1 and 1, and that will be multiplied by vector j. And then we're adding our last term where we'll have one more 2 by 2 determinant, but this time multiplied by vector k. So if we go over to our 3 by 3 matrix here, we're looking at vector k. So we'll cross out the row and the column that that vector is located in, and the remaining 4 values will make up that determinant. So we have -4, 1, and then 1, 3. Okay, so now let's calculate each of these determinants. This will be equal to 1 times 1 minus -2 times 3. 1 times 1 is 1, but then we will subtract -2 times 3, which is -6. So we have -6, and then we're multiplying by I. Then we will subtract -4 times 1. That's -4, and then we're subtracting -2 times 1, which is -2, and that's multiplied by j. And then we're adding -4 times 3, which is -12, and we're subtracting 1 times 1, which is 1. Okay? Now if we simplify, 1 minus -6 is the same as 1 plus 6, so this is equal to 7i, and then we are subtracting -4 minus -2. That's the same as -4 plus 2, so that's -2. But then we are subtracting -2j, so that will become plus 2j. So we'll have plus 2j, and then we're adding our last term of -12 minus 1 times k. -12 minus 1 is -13, so we're actually going to be subtracting 13k. All right, so we'll erase that plus sign, and we'll have minus 13k. That right there is the cross product of vector v and vector u. 7i plus 2j minus 13k. We now have a vector that is orthogonal to both vector v and vector u. All right, but now we also want to calculate the cross product of vector u and vector v, the reverse of that cross product we just found. Now, if you think back to our notes, I did say that when you reverse the cross product, it's also going to give you a vector orthogonal to both v and u, except it will be in the opposite direction of the vector that we just found, the cross product of v and u. So a quick trick that you could do here is just negate each of these terms, and that will give you the reverse of that cross product. Okay, so u cross v would be -7i minus 2j plus 13k. But to show you that that's true, let's just do the cross product again, but I am going to do it a little bit quicker this time. We're going to have vector u cross vector v, and let's set up our 3 by 3 matrix again. We're still going to have I, j, and k in the first row, but then the second and third rows are going to swap placements from what we originally had, because now we have u cross v instead of v cross u. So the components of vector u will be in the second row, and the components of vector v will be in the third row. So we'll have 1, 3, 1, and -4, 1, -2. Okay, now I'm going to do this a little bit quicker here. Starting with I, I'll cross out the row and the column. So we're looking at these 4 values right here. The determinant of those 4 values will be 3 times -2 minus 1 times 1. So we'll have -6 minus 1, and that's multiplied by I. Then we are subtracting the determinant of the remaining values when we cross out the row and column of vector j. So now we have 1 times -2 minus 1 times the negative 4. All right, so we have negative 2 minus negative 4, and that's multiplied by j, and then we're adding the last term, which we find by crossing out the row and the column of vector k, and then the remaining 4 terms will calculate a determinant. So we'll have 1 times 1 minus 3 times negative 4. All right, 1 times 1 is 1, and then we're subtracting 3 times negative 4, which is negative 12, and that's multiplied by k. And if we simplify, negative 6 minus 1 is negative 7, so this is equal to negative 7i. And then we have negative 2 minus negative 4. That's the same as negative 2 plus 4, so that would be positive 2. But then we're subtracting that value, so we have minus 2j, and we're adding that to 1 minus negative 12, which is the same as 1 plus 12, which is 13. So we have 13k, and as you can see, we have the exact same vector that I just described earlier. The vector of u cross v is the same vector as v cross u, except the terms are negated. All right, 7 became negative 7, 2 became negative 2, and negative 13 became positive 13. Okay, so that should confirm what we talked about earlier. If you reverse the order of the cross product, you get the same vector, but in the opposite direction. Okay, whenever you multiply a vector by negative 1, or whenever you negate a vector, you end up reversing the direction of that vector. Okay, so that was our example of calculating the cross product between two vectors. Now you've seen how to do it for two actual vectors, not just the general case. But now what I want to do is take a look at another way that we could define the cross product by analyzing its magnitude. Let's take a look. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so what we're going to do here is take a look at the magnitude of the cross product between two vectors squared. By analyzing what this would be equal to, we're going to be able to learn another way to represent the cross product of two vectors. All right, and the first thing that we can do here is rewrite this magnitude squared as the dot product of this vector with itself, right? If you have a vector and you multiply it by itself via the dot product, we know by one of the properties of the dot product that that's equal to the magnitude of that vector squared. All right, so if we have the magnitude of a vector squared and the cross product of two vectors is a vector, that will be the same as this vector multiplied by itself via the dot product. So that will look like this. We'll have that this is equal to the vector of vector v cross vector u multiplied by itself via the dot product. And so we'll have vector v cross vector u again. All right, and now at this point, what we would want to do is perform the dot product between these two vectors, or essentially the dot product of this vector with itself. And so if we write out what this vector would be equal to using the definition of the cross product, here's what that would look like. I apologize that they're so small, but by the definition of the cross product, this is what vector v cross vector u would look like. So we have that vector multiplied by itself. And remember that the dot product is calculated by taking the sum of the product of corresponding components. So we would take this x component, multiply it by this x component, add that to this y component multiplied by this y component, and then add that to multiplying this z component by this z component, and that would be your dot product. And so at this point, this is where a lot of textbooks will skip some steps, because this is going to be a lot of work. Performing the dot product between this vector and itself will end up becoming pretty messy and involve a lot of algebra, because what you're going to end up doing is squaring each of these components of this vector, right? You're multiplying each component by itself. So really what you'd have here is this. We have the x component squared plus the y component squared plus the z component squared, which as you can imagine is going to become very, very messy and involve a ton of algebra in order to simplify. In particular, this is the end result. So you're going to have some algebra here. And then the result of that dot product will simplify to look like this. You're going to have a quantity of v1 squared plus v2 squared plus v3 squared. And then that's going to be multiplied by another quantity of u1 squared plus u2 squared plus u3 squared. And then you're going to subtract one final term that looks like this. And this is a quantity that is squared. You'll have v1 times u1 plus v2 times u2 plus v3 times u3. All right, so performing this dot product between these two cross product vectors will result in this expression right here after you do a lot of algebra. Now, I don't typically like to leave out steps. I think it's important for you to see all the steps of proofs like these so that you know where your formulas come from. And so I am going to show you what this sum algebra step looks like. But just very briefly, I'm going to put it up on the screen, and when you see it, you're probably not even going to care anyway. You're probably not going to want to look at it. But in case you were curious about what that algebra looks like, here it is. As you can see, it is not fun. I'm going to briefly talk you through it, and then we're going to get right back to our proof, because this is not an algebra video. This is a Calculus 3 video. So I want to get to the final result of what we're going to do with the cross product here. But really quickly, in this first line here, these three quantities are the result of squaring each of the components of that cross product vector. So this is the result of squaring the x component, this is the result of squaring the y component, and this is the result of squaring the z component. Then in the next step here, I just removed the parentheses. So I removed each of those parentheses, and now we have all of those terms listed here. And now I have them color-coded because in the next step, I reorder where they are so that I can group them appropriately so that they can then be factored in a certain way. And you'll notice that I have these red terms here. Those are terms that I added and subtracted as forms of 0 that need to be here in order to do some factoring. All right, so you'll notice that each of these positive terms has a corresponding negative version. You have to do that if you're going to add terms to an equation so that you're not really changing the equation because technically you're just adding 0. Right, this term and this term would cancel out to become 0, this term and this term would cancel out to be 0, and this term and this term would cancel out to be 0. You have to add both versions to the equation in order for you to add terms like that, okay? But then regrouping those terms, we can factor this quantity like this. That's where those two quantities came from that I wrote down previously. v1 squared plus v2 squared plus v3 squared, and then u1 squared plus u2 squared plus u3 squared. And then we have those remaining terms. Now these new color coding here are referring to the next line. Those do not match up with up here. Hopefully that's not too confusing, but then what I did do is pull out a negative from all of those remaining terms that were not in this quantity. So all of these terms right here, you can see that they're negative. Now they're all positive. We pulled that negative out. And then in the next line, I just reordered those terms so that it's easier to see how they factor into this factorization, which maybe you can't see at all. That's totally fine, but I'm telling you, if you were to multiply this quantity by this quantity, you would get all of these terms, just like if you multiply these two quantities together, you would get all of these terms. All right, so you could check that out if you wanted to, but that is how we get from the dot product of that cross product vector with itself down to this line right here, okay? And this is where we pick up in our work. So let's go back to that. I hope you can appreciate all that algebra, but if you didn't follow it, that's fine too. Just know that this right here, the dot product of this vector with itself, does simplify to this expression right here. That's what's important to realize here. Because then what we can notice is that this quantity, v1 squared plus v2 squared plus v3 squared, that is just the magnitude of vector v, but squared, right? We could rewrite it like this. That would be the same as the square root of v1 squared plus v2 squared plus v3 squared squared, because that square root and that square would cancel out, and you would have v1 squared plus v2 squared plus v3 squared. But the square root of those components squared is the magnitude of vector v. And in the same way, this quantity is the magnitude of vector u squared. We could rewrite that to be the square root of u1 squared plus u2 squared plus u3 squared squared, and you can see that we have the magnitude of vector u squared, the square root of the sum of the components squared. Okay, so this is the magnitude of vector v squared, this is the magnitude of vector u squared, and then what do you notice about this quantity? We have v1 times u1 plus v2 times u2 plus v3 times u3 quantity squared. Well, this right here is the definition of the dot product for vector v and vector u. We have the sum of the product of the x components between v and u, the product of the y components between v and u, and the product of the z components between v and u. So we have the dot product of v and u squared. So we can subtract this quantity squared, which is vector v dot vector u. Okay, now we're almost done. We have a couple more things that we can rewrite here to get an interesting result. Let's rewrite these magnitudes squared. This will be equal to the magnitude of vector v squared times the magnitude of vector u squared, and then we're subtracting the dot product of v and u squared. But now, remember, we do have an alternate form of the dot product. It looks like this. The dot product of vector v and vector u is equal to the magnitude of vector v times the magnitude of vector u times cosine of the angle between those two vectors, right? We learned about this in our lesson on the angle between two vectors. This is the alternate form of the dot product. So let's replace the dot product of v and u with this expression and watch what happens. We will have the magnitude of vector v times the magnitude of vector u times cosine of theta, and that whole quantity is squared. And then if we square each part, we'll have the magnitude of vector v squared times the magnitude of vector u squared times cosine squared theta. So this will be equal to the magnitude of vector v squared times the magnitude of vector u squared minus the magnitude of vector v squared times the magnitude of vector u squared times cosine squared theta. All right, and now notice that both of these terms have a common factor of the magnitude of vector v squared times the magnitude of vector u squared. We can pull that out of each of these terms, and here's what we'll have now. We'll have the magnitude of vector v squared times the magnitude of vector u squared pulled out of 1 minus cosine squared theta, right? If we pull this out of the first term, we're left with 1. And if we pull this out of this term, we're just left with cosine squared theta. And now this is where things get really interesting. We can rewrite 1 minus cosine squared theta using a trig identity. Remember that cosine squared theta plus sine squared theta is equal to 1. So if we solve for sine squared theta, watch what happens. We'll have sine squared theta is equal to 1 minus cosine squared theta, right? We just subtract cosine squared theta from both sides of the equation. And what we find is that sine squared theta is equal to 1 minus cosine squared theta. This is our Pythagorean identity for sine and cosine, which tells us that 1 minus cosine squared theta is the same as sine squared theta. So now let's rewrite that. We'll have that this is equal to the magnitude of vector v squared times the magnitude of vector u squared times sine squared theta. And now we are on to our final step, which is to take the square root of both sides of the equation, because if you remember, we are saying that the magnitude of vector v cross vector u squared is equal to this expression. So if we take the square root of both sides and solve for the magnitude of the cross product of v and u, we'll have that the magnitude of vector v cross vector u is equal to the magnitude of vector v times the magnitude of vector u times sine of theta. All right, we just took the square root of each of those values, so now they're no longer squared. We just have the magnitude of vector v, the magnitude of vector u, and sine theta, where theta is the angle between vector v and vector u. And this right here is what we've been working towards this whole time. We have now just found that the magnitude of the cross product between two vectors is equal to their magnitudes multiplied together multiplied by sine of the angle between those two vectors. All right, and so this is a very important formula to know, but we can also use this magnitude to find the cross product of two vectors, right? Remember that any vector can be defined by taking its magnitude and multiplying it by its direction. So if we want to find the vector vector v cross vector u, we should take its magnitude and multiply it by the direction, which we would represent with a unit vector. So in this case, we would say that vector v cross vector u would be equal to its magnitude, which we have right here, the magnitude of vector v times the magnitude of vector u times sine theta, and then multiply that by the direction of that vector, which we would represent with some unit vector, vector u. All right, that's a different vector u than this vector. This is just some non-unit vector, vector u, but this is a vector u that is a unit vector because of that little hat. Okay, you could use a different letter other than u here, but just to stay consistent, I've been representing unit vectors with u, so that's why I used it here again. Okay, but don't get confused between this u and this u. They're different vectors. Okay, and so what we have here is another way to find the cross product between two vectors. So if you know the magnitudes of those vectors, the angle between them, and the direction of their cross product, then you can use this formula to calculate the cross product, but otherwise you will have to use the other method I showed you, which is where you use determinants. Okay, now one more thing that I want to mention about this formula here. Let's say that the cross product between vector v and vector u is equal to 0, or because the result would be a vector, it's the 0 vector. What would need to happen in this equation in order for that to be true, in order for the cross product of two vectors to be 0? All right, and we're assuming that both vector v and vector u are not 0 vectors themselves. They're both non-zero vectors. They have x, y, and z components that are not all 0. That would mean that neither of these magnitudes would be 0. So this is never going to be 0 because of the magnitudes. And a unit vector will never be 0 because a unit vector has to have a magnitude of 1. So it wouldn't make sense for that to be 0, which means that the only way that the cross product of two vectors is equal to 0 is if sine theta is equal to 0, right? Because if you have 0 here, then 0 multiplied by everything else will be 0. So if we take a look at that real quick, when will sine theta be equal to 0? When does that happen? Well, if we're just looking at angles of theta between 0 and pi, because those are the only angles we look at for the angle between two vectors, sine of theta is only equal to 0 when theta equals 0 and when theta equals pi. And if you think about what that means, if the angle between vector v and vector u is either 0 or pi, that means that our vectors either look like this or like this. In this case, the angle between them is 0 because they're right over top of each other. And in this case, the angle between them is pi, or 180 degrees. Notice that in both of these situations, vector v and vector u are parallel, right? They're either pointing in the same direction or pointing in opposite directions. So what we learn here is that when the cross product between two vectors is 0, or the 0 vector, the angle between them is either 0 or pi, which means that they are parallel. If the cross product of two vectors is 0, those vectors must be parallel, which would also mean that they're scalar multiples of each other. Okay, and so this is an interesting result because if we compare that to what we know about the dot product, when the dot product is equal to 0, here's what we learn. When the dot product of two vectors is equal to 0, we know that those two vectors are perpendicular or orthogonal, but when the cross product of two vectors is equal to 0, or I guess it would be more accurate to say the 0 vector, then those two vectors are parallel. All right, so this is kind of a neat thing to make a note of. But now that being said, I wouldn't recommend that you use the cross product as a test to see if two vectors are parallel. It's going to be much quicker and much easier for you to determine that by just determining if those two vectors are scalar multiples of each other. That's going to be way quicker in most cases, but regardless, it is nice to know that the cross product of two vectors is 0 when they're parallel. Okay, but now with that, now that we have this new formula for calculating the cross product, let's just briefly summarize our two methods of finding the cross product between two vectors. Okay, so the cross product between two vectors, vector v and vector u, can be calculated two different ways. This is going to be the most common way that you find it, where you take the determinant of a 3x3 matrix. The first row is I, j, and k, the second row is the first vector's components, and the third row is the second vector's components. And finding that determinant will give you this vector right here, which is the cross product of v and u, Or if you happen to know the angle between those two vectors, the magnitudes of those two vectors, and the unit vector that describes the direction of that cross product, then you can find it this way by multiplying the magnitudes by sine of that angle times that unit vector. Okay, so these are the two formulas that you want to know in order to calculate the cross product. And of course, as a byproduct of this formula right here, the magnitude of vector v cross vector u would just be this portion of the formula. Okay? Now before we close out this lesson, I do want to briefly talk about some of the properties of the cross product, just like I did with the dot product. Okay, so there's 6 different properties of the cross product that we want to look at here. And so for these 6 properties, we're going to be looking at vectors v, u, and w, as well as a scalar c. And our first property looks like this. We kind of already mentioned this earlier in this video, but the cross product of v and u is equal to the negative version of u cross v, right? If you reverse the order of the cross product, you get the same vector, but in the opposite direction, okay? And so it's important to realize this because what that means is that the cross product is not commutative. So the order in which you perform the cross product does matter, unlike the dot product. All right, for a dot product, v times u was the same as u times v. You could reverse the order. That is not the case for the cross product because, as you can see, one of them is a negative version of the other. Okay, so order does matter with the cross product, and that is highlighted by this first property. Now, the second property, you can sort of think of this as your distributive property for the cross product. We have that vector v cross vector u plus vector w is the same as v cross u plus v cross w. All right, so for crossing v by both of these vectors that are being added, we can just cross it by each of those vectors individually and add that together. And that would be the same thing. All right, so we have v cross u right here, and then v cross w right here, and we add them together. Okay, now for our third property, this deals with scalar multiplication. If we have a scalar times the cross product of two vectors, v and u, that would be the same as multiplying that scalar by vector v and then performing the cross product with vector u, or multiplying that scalar by vector u and performing the cross product with vector v. All right, so you can multiply that scalar by either of those vectors first and then performing the cross product, but you do not multiply it by both of those vectors. All right, notice that we don't have c times v cross c times u, it's just one or the other. Okay, so that's how you deal with scalar multiplication for the cross product. Now for our fourth property, we have that the cross product of a vector with the zero vector, or the reverse of that, the cross product of the zero vector with a vector is always going to be equal to the zero vector. And you can see that for yourself if you tried to find this cross product. Since all the components of the zero vector are 0, each one of those little 2x2 determinants are going to give you a result of 0. Okay, and so performing the cross product with the zero vector will always give you the zero vector. All right, now for our fifth property, the cross product of a vector with itself is going to be equal to 0, or the zero vector. And once again, you can see that for yourself. If you try to calculate the cross product of a vector with itself, you would find that all of the terms would cancel out. All right, and that should make sense, because remember what we said earlier, if the cross product of two vectors is 0, then that means that those vectors are parallel. And so if you're crossing a vector with itself, then clearly that vector is parallel to itself because it's just itself. Right? The angle between that vector and itself is 0, so it's parallel to itself, and the cross product of that vector with itself will be 0. Okay? And then finally, for our last property, we have that vector v times vector u cross vector w via the dot product is equal to vector v cross vector u times vector w via the dot product. All right, and this calculation actually has a special name. It's called the triple scalar product. And we'll talk about that more in a future lesson. But just know that there's two different ways to do a triple scalar product, which is highlighted by this property here. Okay, notice that the order here didn't change. We still have vector v, vector u, vector w, vector v, vector u, vector w. We just switched the position of those operations, but we're still performing the cross product first. All right, because that will give you a vector that you can then multiply by another vector via the dot product to get a scalar. Okay, so I hope that makes sense. But with that, Those are all the properties of the cross product that you want to be aware of, and that is also everything about the cross product that I wanted to cover in this video. So with that, that's it for this lesson. But if you do want to see some more examples of performing the cross product, feel free to check out my examples video that I'll have linked here on the screen. And if you have any questions, feel free to leave those in the comments below. But if you don't have any questions, this is all I had for now. So I will see you next time.